Ready. All right. Here we have a first order circuit, right? We've got a capacitor. That's the only energy storage element. And so we're given the circuit, and we're told also that the voltage at 0 minus is 3 volts. Well, by 0 minus, we mean right before this switch gets thrown. Okay, so the voltage across the capacitor is 3 volts right before the switch is thrown. Then we're asked to find Vc of t for all t greater than or equal to 0. So, you know, if I hadn't told you that all first order circuits, you know, can be defined by that first order differential equation, then you would have to go and find that first order differential equation yourself. But that work's already been done. You don't have to reinvent the wheel each time. So that's why first order circuits are so easy. The work's been done already, and there's only one solution. And so my job is to just make sure that this first order circuit looks like the one that I showed you earlier, which had that Thevenin equivalent circuit. So that's the job here, is that I've got to get the Thevenin equivalent circuit. So in my solution, I need to find, right, the open circuit voltage, right, and the Thevenin resistance. And then, okay, so basically I want to look at the circuit from the terminals A and B and find, in fact, I can show it like this. Basically take all of this and replace it with the Thevenin equivalent resistance. All right, and since they're only interested at t greater than or equal to 0, then this switch is closed, right? Because at greater than 0, the switch is closed. So I'm looking at the circuit from the perspective of A and B, and I need to find the Thevenin resistance. I need to find this Thevenin equivalent circuit. So what's the easiest way to do it? Well, remember, there's 3 different ways that you should do it. If you have a circuit that only has independent sources, then you can find the Thevenin resistance by killing those sources. I know, I hate that word. It's not very nonviolent. By deactivating them. I don't know. So what that means, okay, so if, I don't know, that's such an easy word. So kill them. Kill them all. So if I did that, then what does the circuit look like? We've got this 4 kilo ohm resistor here. If I kill the voltage source, what does that mean? It means I set it equal to 0. A voltage source set equal to 0 is a short circuit. So I just killed the voltage source there. And then I've got that 500 ohms here. And then I've got a current source. Well, what does it mean to kill a current source? Set it to 0. A current source set to 0 is an open circuit. So I guess I could kind of show it like that, but it's open. This is just kind of dangling there. So if you look inside here, you know, if you look at this from the perspective of terminals A and B, what's the equivalent resistance? It's just the 4K. Okay, so that was easy. And it is easy to find the Thevenin equivalent resistance when you've only got the independent sources. If we had a dependent source here, remember, it's a lot more work. What we'd have to do is we'd have to find first the open circuit voltage, and then we'd have to find the short circuit current, and then we could just get the ratio of those two, and that would be the Thevenin resistance. But this was pretty straightforward. Okay, but now we need the open circuit voltage. So to get the open circuit voltage, yeah, I'm gonna draw the picture. To get VOC, I need to use this picture, so I'm going to redraw it. 2 milliamps, 500 ohms, and then we've got the 4K, and then the 12 volt voltage source. And then, we've just got a problem. A regular circuits problem of finding the open circuit voltage. Or, just finding the voltage there. So, I don't know, we can use mesh current analysis or node voltage analysis. To me, it looks like this is going to be a lot easier using mesh current. Because we've got a lot of nodes, right? 1, 2, 3, 4 nodes. But we've really only got two meshes. So I'm going to go ahead and use mesh current analysis to figure out the VOC. So mesh current analysis, follow the 5 steps. Remember, do like the Super Kaufman. Draw, so we've drawn it. Label, so that means label the mesh current. So in this case, I've got this mesh current. I have a mesh current here. But since this is open, I actually know that this is, I'll just label it 0. This one, I could label it, I1 because it's the current in mesh 1. But look, we've got a voltage source on the perimeter, so this has to be 2 milliamps. Now, if you had labeled this I1 and I2, that would be fine. We would eventually figure out what they are. But I'm kind of using this idea that since this is open, I know that this is 0 milliamps, and then since this is on the perimeter, this mesh current has to be 2 milliamps. So do like the Super Kaufman, draw, label. Okay, that third step, do like duh, has to do with those dependent sources. We don't have any dependent sources, so I can skip that step. And then S has to do with super meshes. Well, something, I've already used that idea. Super mesh is when you identify a mesh. It's any current source and the 2 meshes on either side. So here's my super mesh, right here. And then in that step, you would not just identify the super mesh, but you need to write out an equation that shows you the current of that current source and how it relates to the mesh currents on either side. Well, this is a little trivial because I actually already used that idea. This is going to be equal to 2 milliamps minus 0, right? 2 minus 0. But if I had labeled these I1 and I2, then it would have been another equation for me to actually solve for I1 and I2. Okay. And then the last thing in the mesh current analysis is to go ahead and apply Kirchhoff's voltage law. So let's do that. Let's see. Let's do it for the super mesh. Kirchhoff's voltage law for the super mesh. Because you can't, so that's where we do it. And I want you to please label it Kirchhoff's voltage law for super mesh, so I know exactly where you're doing it. So we've got minus 12 plus 4K times 2 milli, right? 4 kilo ohms times 2 milliamps. So plus 4K times 2 milliamps. Notice I'm keeping the metric prefixes, but I'm dropping off the units, because as long as your units are volts, ohms, amps, you're fine. So minus 12 plus 4K times 2M plus VOC is equal to 0. All right, so I can just solve this equation for VOC. It tells me that VOC is equal to 12 minus 8, or 4. 4 volts. VOC is 4 volts. Great. So I've solved my problem here. VOC, I know that my Thevenin equivalent circuit, VOC is 4 volts. RT is 4K ohms. All right. So now that I've done the work of getting my first order circuit to look like one of those standard circuits, I can just, boom, apply the solution. Now in this case, it is a constant source, right? It's just 4 volts. If this were a function of time, then I would have to use that more general solution that had the integral. But since it's not, I could go ahead and just apply the solution for the constant source. Okay,